So we did diagonalization the last time, and today I want to get into a few details of where diagonalization is important, how we apply these ideas, and in very different places, right? We'll even see today the idea being showing up in differential equations. We'll see it in the Fibonacci numbers. We'll see it in what else? We'll talk about a little bit about linear transformation as well, right? Okay, so let's say we were doing something along the lines of, so the idea behind diagonalization is being able to write a matrix A into three factors, x, d, x inverse, right? Where this is the matrix of eigenvectors that has columns are eigenvectors, right? And this is the diagonal matrix with lambdas on the diagonal, that is all the eigenvalues on the diagonal, and this is of course is the inverse of x, right? Right. So, and we also stated an important fact that this is possible if and only if A has n independent eigenvectors. Okay. All right. So first, I'm going to talk about something called the steady state. Right. So we saw something along the lines of how do we find, if we have A, how do we find A to the k, right? And the idea behind the steady state is, for example, let's say you have some rule being applied, that is in every time, think of it as time step, right? Or maybe that this A matrix takes from step k to step k plus 1, and we'll see some applications of this idea, so you'll have some idea of what's really going on. But here's the idea. So let's say you have some initial population, right? Initial population u naught, right? And this is some vector that's telling me how many, let's say we're trying to solve a population model where, let's say, the first one relates to the population of some wild animal, let's say snakes, and this is I don't know what eats snakes, let's say rats, and maybe some insects, right? Okay, so let's say these are the three animals in our population, and each of these entries really determine what's going to happen, what's the initial number of these animals living in a particular ecosystem, right? And let's say this A is some propagation model that we've figured out that to find U1, we do A times U, right? So let's say after 5 years, U1 is the population, or let's just keep it to after 1 year, the new population becomes U1. And this is my propagation model, right? So this is the propagation matrix. And so now the question really is, does the population reach some equilibrium, right? Reach some equilibrium. So what does that mean? It means, so U1 is equals to A U naught can be characterized as UK plus 1 is equals to A to the UK, right? But UK itself can be written as A times UK minus 1, which means the whole thing can really be written as A to the K U naught. If you expand all of these UKs up until you reach the first time step, then you see that this propagation model really tells us that in the K plus 1 year, the population is going to be A to the K times the original population. So you don't have to go through each of these individual steps. You can simply do UK plus 1 is equals to AK UK, right? As long as this is just some numbers in a matrix, right? Okay, so now the idea is, does it reach some equilibrium, right? Which means that does it happen at some point that this AK stabilizes, or that this matrix has no effect on these population, right? And so really the question is, does AK turn into some, that AK times UK becomes, so AK times, or rather in another word we can say UK plus 1 is the same as UK as K becomes large, right? Okay, and so this idea of having no effect can be seen as, for the steady state, what really happens is that this has no effect on, so when do we reach the steady state, right? When you don't have, let's say, if UK plus 1 is the same as UK, that means adding another power, a to the k plus 1, u on UK is the same as UK, right? That doesn't change anything with UK, which means this a to the k plus 1 must approach the identity matrix, the n by n identity matrix, right? And then you can have a steady state solution of the system, right? So let me just recap. Maybe I've misspoke earlier, so let me just clarify what's happening. So we have a model. We have some initial population U0, and that's my initial population. We have a rule for finding UK plus 1, which is the population at the after k plus 1 years, and that's just a times UK, which can be then further simplified into a times UK minus 1, which is just a squared UK minus 1, right? Which means it can be further, so a squared, then I can write this as a times UK minus 2, and I can keep expanding these UK minus 2 into a times UK minus 3, and keep doing that until you get to the point of AK U0, right? So you multiply the initial vector by this A matrix K times, and you get the population at UK plus 1. And so the idea is that this is really easy to do when you have a diagonalization, right? Because we've seen that if A can be written as x d x inverse, then a to the k is simply x d to the k x inverse, right? That's something we talked about, that AK is just equals to x dk x inverse. So if you have a model like that, it's easy to find maybe a steady state, because you can easily find powers of this and see if this is going to the identity, or if the identity matrix, or it's not stabilizing at all, it keeps on changing. So there are population models where it doesn't approach identity, and you can have something like cycles where let's say the population of one species increases, causing the other one to decrease, but after some point the population of the other species has become so low that the other species can't survive, and then their population starts dwindling, and then we have this cycling going on, right? So that can also happen. Okay, a specific case can also happen where, let's say, your system is not stable and AK approaches the 0 matrix, right? And so the question is, when can this happen? When does this happen? And this can happen in the situation when your, let's say, so AK, if that is approaching 0, that means x to the dk x inverse is approaching 0. But we already know that this multiplying it by k times has no effect on this x and x inverse, which means what's really going to go to 0 is dk, right? So dk which is just the eigenvalues placed on the diagonals, lambda 1 to the k, lambda 2 to the k, and so on, lambda n to the k. So this matrix must approach the zero matrix, right? And that can happen when each of these individual powers approach the zero matrix. So when does this happen, that an individual number, when multiplied k times, approaches zero? When do powers become smaller and smaller? That happens, of course, in the case when all the eigenvalues are less than 1, when their absolute value is less than 1. So they keep on decreasing and they end up to be 0. So if your system is not stable, then all your species in that system would die, and the uk plus 1 will approach basically just the zero vector, right? Okay, so that's one of the application. Let's take another look at the same idea from the lens of linear transformations. Linear transformation. Let's say A is x dx inverse, right? So let's think about it in terms of linear transformation, in that A is, so if we do A times x, we know that when you multiply A with all vectors, you get some transformation of your space. So let's say my original space was something like this, or maybe let's draw it in a different way. So let's say this was my original space, and multiplying it with A turned it into another space, something like this, right? So let's say if these were the, let's say these were the bases, ample rectangular bases in which the space was being spanned. And now once I transform this, it turns into, let's say, some space of this kind, right? Now the question is that x dx, what A is doing, that same transformation should be done by x dx inverse. But then what are these other matrices doing? What is this x matrix doing, and what is this x inverse matrix doing? These are actually, so the idea is that you can view them as change of basis matrices, right? So let's suppose what this x matrix does is, or x inverse matrix does is, let's say if you're doing A times x, that's the same as doing x d x inverse times x, right? So what is this x inverse doing to x, right? So let's say this is also a change of basis matrix, right? So the first thing that x inverse will do is it will give us the same space, right? But what it will do is it will change the bases in which we were working. So maybe now we're working in, originally we were working in these rectangular bases I and j. Now we're working in sort of these diagonal basis vectors, right? So maybe something like this, right? So this is a basis and this is these two basis vectors, right? But it's still the same space with the shape, looking at the shape and looking at the vector, it's still the same space, right? And so the vectors haven't changed, nothing really, but it's just that we're spanning the same space with different basis vectors. So this is what x inverse will do. So x inverse changes the basis into this, and then this D matrix does the transformation into, does the similar transformation, but it now takes this new basis, right, and it turns it into the same shape that A is going to turn this space into, but the difference now is that this new space is also being spanned by the basis that x inverse transformed A into, right? And so now this step was done by x inverse, this step was done by the diagonal matrix D, and now finally you can see that if I apply x to this matrix, then if let's suppose x is an invertible transformation, right? So which means the inverse exists because this was invertible. If multiplying by x inverse changes this basis to this, then multiplying by x should reverse that transformation, right? Should reverse that basis, change of basis. So multiplying by x then reverses the basis and gives us the same space as the original space. So the idea is that if you go in this direction directly from this space to this space, that's the same thing as first changing the basis, multiplying by the diagonal matrix, and then reversing the basis again, right? So that's a really cool application of diagonalization. And this is not just limited to matrices that are diagonalizable. There's an idea of similar matrices. It's a concept that is very similar, no pun intended, to the diagonalization process, where we say that A can be written as B times C times B inverse, where this C may or may not be diagonal, right? It may not be diagonal, and in most cases it won't be really diagonal, right? So, and the same kind of story will really play out, in which I can just take this whole diagram that we have made, and really what's going to happen again is that this transformation, instead of going from x inverse d and x, it's going to turn into something like so this will be B inverse C and B, right? So A is equals to B, C, B inverse. And notice that the order is different, right? Because when you multiply, you start off multiplying from this side. So AX should be equals to first multiplied by B inverse, then multiplied by C, and then multiplied by B, right? Okay, so then what's the nice thing about diagonalization? What's the difference between similar matrices and this idea? So if that's really if this is really the same kind of concept, what's the crucial difference is getting a diagonal matrix, right? What's the only difference that we can see is that this C is not diagonal, but this D matrix is a diagonal matrix, right? And so how do we see what's nice about this diagonal? Of course, the nice thing is when you multiply a diagonal matrix, right, lambda 1 to lambda n, each of the components, whatever these components that you have, will just be multiplied by lambda 1, which means that in this transformation, you're only scaling the eigenvectors, which means if this was an eigenvector and this was an eigenvector, then these will just be stretched out a little bit, right? Stretched or compressed, whatever that scaling might be. But the nice thing about this characterization is that this D matrix will just scale the eigenvectors, and then you can reverse the process. But in this transformation, that may not be the case. C matrix might not just scale them, it might rotate them, it might turn them around, it won't keep them invariant, right? So the eigenvectors like this might, the eigenvectors which were maybe in this case not along these bases, maybe something like this, will now look something like this. They might have been rotated, right? Okay, so that's the view of diagonalization from the lens of linear transformation. So in this case, by the way, we call A and C are similar matrices, right? And the idea of similarity is that they perform the same linear transformation, right? And the reason they do that is, notice that they're both doing the same transformation but under different bases, right? The C matrix was transforming the space under a different matrix. The A matrix was transforming the space but in a different basis. Okay, so that's another application of diagonalization. Okay, let's look at the Fibonacci numbers. The Fibonacci numbers. So if you remember, if you've ever come across these numbers, they're a sequence, they're a very easily produced sequence, and the rule is that UK, or rather f, the k plus 2, is the sum. The new Fibonacci number is the sum of the previous two Fibonacci numbers, right? So, and we need some values to, at least two values to start from, right? Because we can't find the next number until we have two initial values. So the first, let's just say we start from 0 and 1. And so the next number will be the sum of these two numbers, which is 1. And the next number will be the sum of these two numbers, which is 2, 3, 5, 8, 13, and so on, right? So this is the Fibonacci sequence. And if you want to find, let's say in this manner, if you want to find F50 maybe, then you have to go through finding F2, then F3, and then go through the entire process and find F50, right? But using diagonalization, there's a easier way of performing the same application, and let's see how. So first we're going to use the same rule, such as UK plus 1 is equals to A UK. We're going to turn it into this equation, and the way to do that is to define this UK plus 1 and UK as follows. So we're going to say the rule is that each UK is going to have the original, the kth Fibonacci number and the k plus 1 Fibonacci number. So this is some A matrix. We don't know what these entries are, so this is A. But for this one, this is going to be Fk plus 1 and Fk, which means UK plus 1. If I want to find UK plus 1, then it should contain the k plus 1 Fibonacci number and then the k plus 2 Fibonacci number. So this is going to be Fk plus 1 and Fk plus 2. Sorry, Fk plus 2. So now, how do I write some entries in this matrix such that we get this rule and such that the equation makes sense, right? So I want to make this rule Fk plus 1 is equals to Fk plus 1. Fk plus 2 is equals to Fk plus 1 plus Fk. So I have these two numbers, which means for the first entry, I just need, if you think about it in terms of the rows, taking some linear combinations of the row. So I want 1 time the first entry and 1 times the second entry. So this first row is going to say Fk plus 2 is equals to 1 times this, Fk plus 1, plus 1 times this, which is Fk. And now I want to write some entries here, which also makes sense. But if I put any non-zero number here, I don't really have access to Fk minus 1, right? So Fk plus 1 should be equals to Fk plus Fk minus 1, but I don't have access to this number. So what I can really do is that just put a 1 here and a 0 here. So the second row is just telling me, that Fk plus 1 is equal to Fk plus 1, which is fine. We're assuming that at this point we already know what the entry is, right? What the k plus 1 entry is. So the system has now turned into UK plus 1 is equals to A times UK, right? And just as we did in the last time, we can just write this as A to the k u naught, right? So we can write this Fk plus 1 Fk as A times UK minus 1, and then I can write this as A times UK minus 2. So I can write the whole thing as A to the k u naught, right? Okay, and so what's the advantage of that? So let's see what's going to happen. Fk plus 2, Fk plus 1 is going to be equals to, assuming that I can find a diagonalization of this, let's say assume we have a diagonalization, then I can write this as x d to the k x inverse, and then the original numbers, which were what? Which were 1 and 0, right? So the original numbers u naught was just, the first number was 0, the second number was 1. So if I can find this diagonalization, I'll be done. I can just find the kth one. So if I want to find f50, that would just mean doing x d to the 50 x inverse times 1, 0, right? That's how I can find, sorry, u50, right? Okay, so let's try it out. Maybe let's say we want to diagonalize a equals to 1, 1, 1, 0. Let's diagonalize it. Let's try to find the eigenvalues and eigenvectors. Okay, so for the eigenvalues, I know I have to solve determinant of a minus lambda I is equals to 0. And so this is going to become, I want to find the determinant of 1 minus lambda. 1, 1 minus lambda is equals to 0. Let's find the characteristic equation. 1 minus lambda minus 1 equals to 0. And so this becomes minus lambda minus plus lambda squared minus 1 equals to 0. So we have lambda squared minus lambda minus 1 equals to 0. Now, do I find distinct eigenvalues or not? Let's see. We can check using, this is just a quadratic equation. We can check using b squared minus 4ac. And I have, what's b squared? That's minus 1 squared minus 4 times 1 and minus 1. So this is giving me a positive number, 1 minus 4, sorry, 1 plus 4, which is 5, right? And so my values, lambdas, are going to be is equals to the using the quadratic formula, which is minus b. So 1 plus minus square root, and I already know b squared minus 4ac, so I just write 5 here, divided by 2 times a, which is 2, right? So I have my first eigenvalue is 1 plus square root 5 upon 2, and my second eigenvalue is 1 minus square root 5 upon 2. Okay, so that's the easy part. Now we find the eigenvectors associated with it, right? Eigenvectors. So the eigenvectors for this one, so what we have to do now is we have to solve a minus lambda I, x is equals to 0. So we have to find the null space of this matrix. So this will be 1 minus, let's do it for lambda 1 first. So it will be 1 plus square root 5 upon 2. And this is turning slightly ugly, but let's just power through this. 1 and then minus 1 plus square root 5 upon 2. Okay, let's write this down. What is this going to be? So this is 2 minus 1. So this is 1 minus square root 5 upon 2. This is 1, and this is minus 1 minus square root 5 upon 2. And let's now do let's try to find the eigenvector. So I have, let's augment this with the 0 vector. Okay, I should really get, notice that this is just, I should really get the second row to be 0 because I should only be able to get one eigenvector, right? So let's see what we get. Let's see, if I multiply this equation by 1 minus square root, so let's say R2 minus, what's this factor going to be? This factor, we can make it into 2 over square root, 2 over 1 minus square root 5 times R1. So the second entry is going to be 1 minus, so this first entry, the first row is unchanged, 1 minus square root 5 over 2, 1. This entry is going to be 1 minus 2 over 2 over 1 minus square root 5. I've just taken the reciprocal. And in the numerator, I have 1 minus square root 5 upon 2. So these cancel out, this cancel out. 1 minus 1 is 0. Okay, what about the second one? We have the 1, 1 minus root 5. That's correct. So 2 cancel out, 1 minus. Okay, that cancels out. So I have minus 1 minus square root 5 over 2. And then subtract from that minus 2 times 1 minus root 5. Okay, and so, yeah, I think I'm just messing up arithmetic, which is really something that I should not be doing. 1 minus 1 minus square root 5, and then 1 minus square root 5 minus 2 times 2, which is 4. So what do we get here? We get, this is a minus b, and a minus b and sort of a plus b, right? So I can write this as minus square root 5 plus 1 and minus square root 5 minus 1. So this is a plus 1 and a minus 1 minus 4. I think we might just get this to be 0. And what do we have here? So this can be written as a squared minus b squared, right? So minus square root 5 whole squared minus 1 squared minus 4. Yep. Whatever is over here. This is 5 minus 1 minus 4. So the numerator is 0. I have successfully gotten a 0 here. Okay, perfect. So the second row isn't really helpful. The first row is telling me that 1 minus square root 5 over 2 x1 plus x2 is equals to 0, which means x1 is equals to what? Minus, so I can write this as x2 is equals to negative 1 minus square root 5 over 2 x1, right? Yeah, that seems correct. Or let's do it in terms of x1. So I have negative x2 here. So whatever, let's call this, so I will have over here, I'll have 2 over 1 minus square root 5 with a negative sign times x2, right? So x2 goes on the other side, I get a negative sign, and then I just divide and multiply. So let's complete this computation. Let's rationalize this. I get x1 is equals to, if I multiply, divide by 1 minus square root 5. So minus 2, 1 minus square root 5 divided by 1 squared minus square root 5 whole squared x2. And this is going to be minus 2 minus square root 5. So minus 2 minus square root 5 divided by, what do I get here? I get 1 minus 5 x2 is equals to negative, sorry, I should have a negative 2 here. So negative 2 root 5 divided by negative 4. And now we can cancel the signs. So we can cancel these negative signs, and we can also cancel these 2's by this 4. So we get 1 plus square root 5 over 2. And notice that this was simply the eigenvalue we started off with, right? 1 plus square root 5 upon 2. So what we've gotten is that x1 is equals to lambda 1 times x2. So the correct eigenvector is lambda 1 x2, x2, and we take x2 common, I get lambda 1, 1, right? So that's really nice. This is the eigenvector. And we can do the whole computation for the second eigenvector as well, but I'm just going to guess that this is going to turn out to be lambda 2. So I'll have x, the second eigenvector for lambda 2 is equals to 1 minus square root 5 upon 2 is just going to be x2 times just this lambda 2 and 1. So these are the eigenvectors. Okay, but we've sort of lost sight of the problem. What were we doing? We started off from finding the Fibonacci numbers, and this diagonalization process has taken us to this extent that we found the eigenvalues and found the eigenvectors. But now our job is almost done. So we can write A is equals to x dx inverse, which means I can put the first eigenvector here, which is lambda 1, 1. Second eigenvector here, lambda 2, 1. The D matrix over here, which is, sorry, the D matrix over here, which is just lambda 1, 0, 0, lambda 2. And then the inverse of this matrix. Let's try to find the inverse of this matrix. What's the determinant going to be? The determinant will be just lambda 1 minus lambda 2. So 1 over lambda 1 minus lambda 2. And then this will just be 1 lambda 1 minus lambda 2 and minus 1. So this is just x dx inverse. I'm not going to simplify this, just leave it just like that. And so now we can find F50. F50 is simply do a to the power 50, but that's just lambda 2, 1, lambda 1, 1, lambda 2, 1, and then over here I have lambda 1 to the power 50, lambda 2 to the power 50, 1 over lambda minus lambda 2, 1 minus lambda 2 minus 1, lambda 1. And remember, if F50 is going to be found by A50, right? So U50 is going to be A50 times U0, which means we multiply this entire thing. So let's just copy this down, right? We multiply this entire thing by the initial vector, which was 1, 0, right? And this will give me F50, and this will be F. So F51, this will be, did I do that correctly? No, this will be F50, and this will be F49, I suppose. Yeah. Okay, and so let's see how this works out. This will be, what will I have here? So let's see, we can do this. So all we need to do is find the first row of this entry, right? So F50 will be given by, let's try to multiply this perhaps. So what do we get when we multiply this? I get lambda 1 to the power 51. I think this should be, I think I've made a small mistake of putting the signs incorrectly. So U100 should be, no, this is fine. U100 is equals to A100. No, that's fine. It's only that this is going to be F50 and F51, I suppose. Okay, and so to find F50, I need to find the second entry of this one, right? F51, F50, and this lambda 1, lambda 2. If we multiply these two, I get lambda 1 to the power 51, I suppose. But I'm interested in the second row, so yeah. So lambda 1 to the power 51, and then we have lambda 2 to the power 51. This is just lambda 150, and this is just lambda 2 to the power 50. And I have 1 over lambda minus lambda 2 going on here, and I can just multiply this matrix by this vector as well. So I get 1 here, and I get minus 1 here, right? And so this, now let's just find the second row of this entry, and this is going to be, I don't need these two, I can ignore these, and this is just 1 over lambda 1 minus lambda 2. This is 1 over lambda 2 minus lambda 1, and this is lambda 150 and lambda 250. So F50 is going to be something like, if I multiply lambda 150 by this, so lambda 150 upon lambda 1 minus lambda 2 plus lambda 2 to the 50 upon lambda 2 minus 1, which I can just write as lambda 1 minus lambda 2 and just change the sign here, right? So there we have a simple, well, took some time, but now we have a formula that gives us the 50th Fibonacci number, which is lambda 1 to the 50 minus lambda 2 to the power 50 divided by lambda 1 minus lambda 2. And that's how. Now, this was maybe till F50 you could have gotten here faster than I have, but I can use the same formula for F1000 as well, right? It will just be lambda 1 to the 1000 minus lambda 2 to the 1000 divided by lambda 1 minus lambda 2. So this difference of eigenvectors, eigenvalues, is playing a role in the Fibonacci numbers. So that's the application on Fibonacci numbers. And really it's an application on any sort of system that you can write in terms of uk plus 1 is equals to auk. Right? And we're going to look at now another application in differential equations. And differential equations and linear algebra are really very closely related, right? And we'll see that today. So first, let's consider two things. The first thing that we're going to consider is what is a, let's try to solve a simple differential equation such as of the form u du dt is equals to a u, right? That's a simple differential equation and that is a solution, or so let me just put lambda here. And to solve this differential equation, we just integrate both sides and we get something like log of u is equals to lambda u plus c, but we can write this thing as u is equals to, sorry, lambda, did I do this correctly? Yeah, so I can write this as c lambda c to e to the lambda u, right? That's the, wait, what did I just do? Sorry, the solution is going to be equals to lambda t plus c, right? So yeah, u is equals to c times e to the lambda t. That's the solution of this differential equation, and you can check that by differentiating both sides. So du by dt, if I differentiate this, we're just going to get c lambda e to the lambda t, and that's just giving us this. Yeah, and we can satisfy this c comes from satisfying some initial condition, right? So u0 perhaps. So let's say u at time 0 is given to me by some u0, and we can then rewrite this equation as u equals to u0 e to the lambda t, right? Okay. Right, did I do this correctly? Du dt is equals to c lambda e lambda t. Right, so du dt is then simply u0 lambda e to the lambda t, and we can see that that's just the same as u being multiplied by lambda. So if I multiply u by lambda, lambda u is just going to be u0 lambda e to the lambda t. Right? That's a very simple differential equation that you can solve using basic calculus. Okay, and let's now look at systems of differential equation, right? Let's say I have a system of differential equations. So for example, I have u1 du1 by dt is equals to lambda 1 u1 plus lambda 2 u2, and I have du2 upon dt as lambda or alpha 1 u1 plus alpha 2 u2. Now this is not as easy to solve as the first equation. The reason is there is a coupling of variables, right? There's a coupling of variables going on, in that the differential equation for u1 involves both u1 and u2, and the differential equation for u2 involves both u1 and u2. So to solve this system, you need to solve this system first, but to solve this system, you need to solve this system first. So following this simple technique won't really help us in this case, right? But we can rewrite this entire system as follows, right? I can write this as a matrix vector equation. I can say that u1 prime and u2 prime is equals to some matrix A being multiplied by u1, u2. So I can view this vector as u, and then this as a vector differential, right? So taking the derivative of this vector gives us this vector u prime. And then how do I fill up this matrix A such that I have both of these equations satisfied? So the first entry for this is lambda 1 and lambda 2. So we have the first equation satisfied and alpha 1 and alpha 2. So you can multiply this matrix vector equation and you will see that you get, in the first row you will get this equation, and in the second row you will get this equation. So we've really turned our problem into trying to solve u prime is equals to au. So let's keep this on the side for a moment. I'll talk about how to solve this system, but let me identify another point, that any higher order linear system can be converted into any higher order linear differential equation can be converted into a system of first order linear differential equations, right? Linear differential equations. And so this system was a first order system, right? Because this was just the first derivative, this was just the first derivative, and it was a linear system because it's linear in u1 and u2. So now we're saying something different. We're saying if we have a higher order differential equation, we can convert it into a system of first order systems. And let's see how that happens. Let's consider the linear differential equation u prime prime plus a u prime plus u is equals to 0. Let's say I have this differential equation. How do I convert this into a system of linear differential equations, first order linear? And the way to do that is to consider a change of variables. So what we're going to do is we're going to call u1 as u prime. And now notice that if I do u2 prime, I'm going to get, u1 prime, I'm going to get u double prime, which I can label as u2, right? So u1 is equals to u prime, u2 is equals to u double prime. And now I can write an equation in terms of u1 prime and u2 prime. So this is my vector, which is u prime, and my original vector is going to be u1 and u2, right? And so now I just have to fill these entries. What is this matrix going to be? Okay, and this matrix entries should make sense in terms of this equation, and this equation. So what is u1 prime in terms of u1 and u2, and what is u2 prime in terms of u1 and u2? Okay, so u1 prime is simply u2, right? So u1 prime I can just write as nothing of u1 but 1 times u2. And what about u2 prime, right? Sorry, I've done this incorrectly. Let me change these equations. I'm going to write u as u1, and I'm going to write u2 as u prime, and this will be, so u1 prime, and this will be just u prime. Okay, let me redo this. So the change of variables that I'm going to start off with, I'm going to start off with this variable and call it u1. So u1 is equals to u1 prime, and u1 is just equals, just confusing myself. Let's see. So u1 is equals to u, and now if I do u1 prime, I get u prime, which I can now label as the new variable u2. And then u2 prime is just u1 double prime, which is just u double prime. And now I can write this equation. So u1 and u2, in terms of u1 prime is just 0 and 1. So u1 prime is just u2, so that's 0, 1. What about u2 prime? u2 prime is u double prime, but I don't have u1, that I haven't given this variable any new name, right? What about this variable? How do I get an equation for this variable? Well, that's where your original differential equation comes into the picture. The original differential equation tells me, if I rewrite this, it tells me that u double prime is negative of au prime and negative of u. And u prime we've already labeled as u2, so I can write this as negative u2, and u I have labeled as u1, so this is u1. So notice I have kept the differential on one side and kept the linear terms on the other side, right? They did not have a derivative on them. So now I can say that u double prime, which was equals to u2 prime, is just negative 1 times u1 and negative a times u2. So I've done this in a confusing way, but hopefully you get the idea that you start off from renaming the first variable and get to the last variable, but for the last variable you don't rename, you just use this equation to get a equation for that. So again, I've turned it into a system u prime is equals to au. Right? A higher order equation, this was just a second order linear differential equation, which I have now turned into a system of first order linear differential equations. Right? Okay, and so the question now really is, how do we solve this? And the idea is really neat. The idea is we're hoping, let's say again, this is an application of diagonalization. So let's say A is diagonalizable, which means A can be written as x lambda or just t x inverse. Okay, what does that give us? At this point, I'm going to do a change of variables in this case. And notice that this equation, again, this equation is a coupled equation, right? If it's not coupled in, well, this is sort of nicer in that you can solve for, actually no, it's coupled. u1 prime contains u2, and u2 primes contains u1 and u2. So this is a coupled differential equation, coupled system. And now we're going to do something that is going to decouple this system. That is, we're going to consider the change of variables. U is equals to xv. Okay, and what does this give us? This gives us that u prime is equals to au, this system. If I use this change of variables, u is equals to xv, then what do I get? Then I can rewrite this system as so I can write this as u inverse, v is equals to x inverse u, right? And what is u prime going to be equals to? U prime will be equals to x, since this has only numbers, it's going to be xv prime. So the left side is simply xv prime, and the right hand side is, if we have x d, the diagonalization of xt inverse x inverse u, we know that x inverse u is just equals to v. So we have xv prime is equals to x d inverse v, and now I can multiply both sides by x inverse. If I just multiply x inverse x v prime, x inverse x d inverse v, this just gives me v prime is equals to d, why did I have a d inverse here? This is just d. So this is now my new differential equation that I have to solve. This is, I do a change of variables and I get v prime is equal to dv. But at this point you should be asking, we wanted to solve u prime equal to au, we just changed that problem into solving a new differential equation, right? What's really the difference? This is u prime, v prime, a, t, u. The difference, of course, is that this is a diagonal matrix, and that if I have v1 prime, v2 prime, then this is just lambda 1, 0, 0, lambda 2, which are the eigenvectors, and this is just v1, v2, which means this system, the solution to this system is simply, this is v1 prime is equals to lambda 1 v1, and v2 prime is equals to lambda 2 v2, which means the only thing that has happened is that we've converted this system. The nice thing that has happened is we've converted it into two equations of this form, of this original form. V prime, u prime is equals to lambda u. And we know how to solve this. The solution to this system is u equals to ce lambda t, right? So the solution to both of these problems are going to be, let's say, c1 lambda 1, sorry, c1 e to the lambda 1 t, and the solution to this problem is going to be c2 e to the lambda 2 t, right? That's the solution to both of these equations. And now we can revert back the change of variables. So u was equals to xv. So since u is equals to xv, we can write x times v is just c1e lambda 1t, c2e lambda 2t, and that's my solution to the differential equation. So I just need to find the eigenvectors and eigenvalues, and then this is my solution to u. And we can write this whole thing actually very neatly by writing this as, we can characterize this whole thing as, so if this is v1, v2, the solution v1, v2 can actually be just written as e to the lambda t, where this is now a matrix, right? This is not just a number, this is called a matrix exponential. And we just put the entries c1, c2 here. And so what I mean by e to the lambda t is simply e to the lambda 1t and e to the lambda 2t. So that's my c1, c2, and that's v1, v2. And furthermore, if you really notice what happened is, how did we get this c1, c2? Notice that this happened. How did we get this v1, v2 actually? This v1, v2 was given to me by f. So v1, v2 is actually given to me by x inverse u, right? So what's really happening is this whole equation can be written as u1, u2, since I need to multiply by x here, right? So this becomes x times e to the lambda 1t, 0, 0, e to the lambda 2t, c1, c2. But now I can write this as, how did I solve this equation? This is x e to the lambda t, x inverse, and then this c1, c2, right? This, how do I get this c1, c2? This is just simply the original initial values, right? Let's just write them as c1, c2. So that's my solution to this problem. Okay. I'm hoping I've done this correctly. Anything missing from this? No, I think that's the right way to do this. Okay, and so we can write this thing. We actually call this the matrix exponential of A, right? We call this e to the at. So we can write this whole solution actually as u vector is equals to e to the at, and we know where the c1, c2 comes from. The c1, c2 comes from the initial value of u, right? So from u0, which means I can write this as the value of the vector at time 0. So this is the solution of the system of differential equations written in matrix form, with this being the matrix exponential. So remember, what was the solution to my just one differential equation? It was u is equals to e to the lambda t u0, and I've written my solution to the system in terms of this matrix exponential, right? This is the matrix exponential, and that's a really cool idea if your matrix is diagonalizable. Actually, another way of writing the matrix exponential is to write it as e to the at equals to I plus at plus half at, I think, squared plus 1 upon 6. Let me see if I'm doing this correctly. This is just this. So 1 upon 6 a cubed t cubed plus so on, right? And this is just very similar to the exponential function, right? Which is just summation x to the n upon n factorial, which is just 1 plus x squared upon 2 factorial plus x cubed upon 3 factorial plus so on, right? And you can just put an entry here, e to the lambda x, which will just be summation lambda x to the n upon n factorial, and this will give us 1 plus lambda x plus lambda squared x squared upon 2 factorial plus so on. So this is really, but notice that these are numbers here, but this is a matrix, right? If you want to do this infinite expansion, you will have to find infinitely many terms. But the nice thing is that this can be written as if it's diagonalizable. You can easily write this as x e to the lambda t x inverse, right? Okay, and so that's the application of diagonalization to differential equations. So this was quite a different lecture from our previous lecture. We talked about lots of different ideas, linear transformations, Fibonacci numbers, differential equations, and hopefully you've gotten some idea of how diagonalization is used, and hopefully that's useful for you when you take more advanced courses which use linear algebra ideas and apply them in different applications. So that's it for today. Let's just end the lecture here. Thank you. Have a good